So we know how to calculate the equilibrium constant, which is going to be the ratio of the products to the reactants when we are at equilibrium. However, what about when we're not at equilibrium? How can we figure out how our reaction is going to shift? Well, there's a few applications where we might need to use this. For example, the Haber process. The Haber process is a very powerful chemical reaction that takes atmospheric nitrogen and some hydrogen and creates ammonia, which this is very necessary for modern fertilizers. Without the ability to produce a ton of ammonia, we wouldn't be able to produce enough food for all the people on Earth. So this process is extremely important. And it can be challenging because atmospheric nitrogen and hydrogen don't make that much ammonia. And so we need this reaction to proceed, and when we're running this reaction in an industrial setting, we might need to keep tabs on where is the equilibrium at. Because if it hits equilibrium, well, we want to dump in a lot more nitrogen and a lot more hydrogen in order to get this reaction to push more to the right. We're trying to produce as much ammonia as possible. And so we might need to figure out the reaction quotient, which is basically a snapshot of where a reaction is currently at in regards to equilibrium. And that's going to be figured out the exact same way that the equilibrium constant is figured out. And then we can just compare those numbers. So we would probably have sensors that would detect how much nitrogen and how much hydrogen we would have and how much ammonia, and then automatically spit these numbers out, give us a reaction quotient, and read that to an engineer. So this is going to be figured out using that same reaction, that same equation. So that would be NH3 squared, that's my products, divided by H2 cubed times the concentration of the N2. So for this reaction, that would be 3.5 squared divided by 9 cubed times 5. Now what would that be? That's going to give us 0.0034. And we're saying our equilibrium constant here is 0.5. So is this going to shift to the right or to the left? Well, this should be pretty straightforward to figure out because this is just a ratio of the products to the reactants. So if our number is smaller than K, well, that means that we've shifted towards the reactants, right? If our number is larger than K, if Q is greater than K, then we will shift. We have shifted. Our Q is more shifted towards the products. And so the way we can easily figure this out is we can just put up a number line, 0 to whatever. In this case, 0 to 1. And halfway on this number line would be K, right? If my Q is to the left of K, so it's going to be way down here, then my reaction will want to shift to the right. My Q always wants to go towards K. And so if I put this on a number line and see which direction would we have to go to get to K, then my reaction, so if I have to go this way on the number line, if I have to go to the right, then my reaction is going to shift to the right. So let's look at another one just to finalize that idea. We've got 2 CO2 making 2 CO and O2. We've got an equilibrium constant of 3.1 E negative 18. Now let's calculate our reaction quotient. That's going to be CO squared times the O2 divided by CO2 squared. That's going to get me 0.48. Now if I put that on a number line, let's put that on a number line. I don't even want to think about it until I've got it on a number line. My K is going to be very, very small. It's going to be way down here. So that's K. And my Q is going to be almost at 0.5. And so for Q to get to K, it's got to move to the left. So which way is my reaction going to shift? It's going to shift to the left. It's going to make more CO2. There we go.